Hello everyone, my name is Tal, and I'm here with my partner Said. In the next 10 minutes, we will take you through a simulation experience that we will credit on grouping of a population based on data from New York City. But first, let us begin with an overview of what we will discuss about today. First, we will give you a brief breakdown about COVID-19 for those who forgot, followed up by a timeline of the disease since its first case up to last month. Next, we will present our goal for this project. Now, doing model like this will not be much effective without discussing our assumption. Finally, we will present our simulation with the conclusion and wrap it up with the sources that we used. Background. On 31 December 2019, group of cases of pneumonia of unknown cause in the city of Wuhan, Hubei province in China, was reported to the World Health Organization. From that point in time, the world was soon to introduce to one of the biggest crises he ever faced together. In January 2020, a previously unknown new virus was identified, subsequently named the 2019 novel coronavirus, and samples obtained from cases and analysis of the virus genetics indicate that this was the cause of the outbreak. This coronavirus was named COVID-19 by the World Health Organization in February 2020. At that point of time, the virus continued to quietly spread around the globe while still to be studied. On 30 January 2020, the World Health Organization declared a public health emergency of international concern and later declared a pandemic on 11 March 2020. As of April 2021, more than 142 million cases have been confirmed. Just a few months before that, as of December 2020, there have been more than 67 million confirmed cases, including more than 1.5 million deaths, reported to the World Health Organization. To the present, the death toll has been doubled, with more than 3 million deaths attributed. COVID-19 considered to be one of the most deadliest pandemics in history ever to be recorded. Here, we can view the timeline of the progress of COVID-19 since the first symptoms throughout recent months. As just said, the current reported death rate that was reported to the World Health Organization is more than 3 million worldwide. The graph shown here is the death rate since March of August 2020 in New York. We can clearly see that the outbreak through the first few months and how it is balancing as the months go by. Next, my partner Said will discuss about the simulation. Said?
Thank you, Tal. Before moving into our simulation, we wanted to discuss one of the journals that we looked into that was published in the Journal of Simulation. It looked into topics for simulation in order to reduce the impact of COVID-19. This article, published in 27 March 2020, delved into possible decisions that simulation can give further insight into. The reason that we liked this article was that the authors also discussed possible modeling techniques for each decision, and it refers to studies based on it. The authors gave us 11 decisions in the original article. Here we are going to discuss 3 of these decisions very briefly. Decision 1, quarantine strategies that can be used. The authors talk about an article by Sharera et al. That demonstrate that quarantines has a significant impact on the spread of Ebola. Since the spread of the virus at the local level is affected by networks, hence agent-based modeling is more suitable according to the authors, since it can model the interaction between individuals through the networks. Decision 2. Modeling of social distancing and quarantining can be treated as a spatial transmission problem with a variety of modeling techniques available. This can be done at a local level using a system dynamics model or by modeling individual agents in the population using agent-based modeling, including behavior rules on their movement and hence the spread of the disease. Decision 5. Agent-based modeling seems most likely work well at modeling these decisions, which is targeting vaccinations according to Lee et al., although system dynamics could also be beneficial for Dr. Aras in 2013. In a new epidemic scenario where vaccinations will become available during the epidemic and it will take some time to ramp up production, There is also a need to target the initial vaccinations at sectors of society that will have the most impact. So now we want to discuss our journey through the project. So our initial goal was to compare the efficacy rate of two vaccines, Pfizer and AstraZeneca, through using two distinct geographical locations, Israel and New York City. However, we had some trouble obtaining specific data pertaining to the locations and the administration of those specific vaccines. Also, we came to realize some of the issues that might arise when comparing the efficacy rate of two vaccines. We realized that the vaccine efficacy rate that we wanted to employ as a constant based on the FDA definition in our model was actually based on the comparative likelihood that an individual with the vaccine is more likely to survive compared to a person without the vaccine. The issue arises upon realization that the same group of people are not used in trials for distinct vaccines, and also the timing of running these clinical trials drastically impact the constant number that our assumption would so heavily rely on. We then decided to create a model that will visualize the spread of the virus on a hypothetical population. We would be able to observe the contagion, recovery, and death based on these preset parameters. We would then introduce a vaccination parameter that would allow us to compare the two sets of data to draw conclusions from. However, we were not able to implement changes in the code that would give us a vaccinated population from the middle of the time series that we were running. So in the end, we had to compromise into looking into the models in which nobody had vaccines or everyone who were vaccinated. So our modified goal then became to achieve a platform that categorizes a population into groups of recovered, infected, and dead based on COVID-19 parameters, which are primarily obtained from NYC data. Now, our model has a list of assumptions that I would like to briefly go through. So R0 is the average number of people who will contract a contagious disease from one person within that disease. 3.28 is the median value obtained for COVID-19 per CDC. Incubation period according to CDC is 2 to 14 days, and we have chosen it to be 7 days. The percentage of population that will show mild to moderate symptoms is 80%, and all of these people in the model will recover. Those who exhibit mild symptoms will recover in 6 days, and those who exhibit moderate symptoms will recover in 16 days. Percentage of population that will show severe symptoms is 20%, and some of these people might die in the model. Those who will recover from severe symptoms early will recover in 35 days, and those who will recover from severe symptoms late will recover in 45 days. The first group of who will not recover from severe symptoms will die in 17 days. The second group of people who will not recover from severe symptoms will die in 59 days. Fatality rate is assumed to be 0.0356, which is fatality rate in NYC in January 2021. The average time between successive cases in a chain transmission is 5 days. The population of this simulation is 18,823, which is NYC's population in thousands. The reason we use this is because that using NYC's original population was creating difficulties for the model to run, given the number is so big. Also, instead of a patient zero, the model assumes 735 initially affected. This is currently NYC's COVID cases in thousands. So now we can take a look into the simulation. Okay, so the red represents people who are being infected by the virus, and due to the golden spiral method being used, the contagion is spread from center outwards. The assumption of 735 patient zeros drastically affects most of the population given the R0 value of 3.28, and then we can eventually see recovery in green as well as death in black. Also, the module assumes an upper bound of people who can be infected or recovered, which is the population itself. Therefore, the number of people, if it ever exceeds the population in a given wave, the model ensures this does not happen. This is why there remains an infected core after day 45 around 50, which we can assume that would recover further. The source code that was used to implement this model is provided in the sources cited. So looking into a similar model next, this version of the model uses very similar techniques to the previous one. However, here it is assumed that everyone in the population has been vaccinated. So death should be pretty rare in this version of the model. Some of the assumptions in made in this model are the death rate is 970 out of 90 million as per data obtained from Vaccine Adverse Event Reporting System database. Those who will die within a week, whether from illness related to the vaccine or other health issues. I was not able to find any detailed studies on this, but it should not be assumed that COVID 19 vaccines itself was the cause of death for this group of people. We can observe a similar pattern in this model as well, despite some of the parameters being drastically altered. This is again due to the built-in mechanism of the model that ensures that infected or recovered never exceed the population limit. So that is why we see the center core again. Uh, some notes on the visualization. Here, the golden spiral algorithm is used, which ensures that the spread occurs from center outwards, and this is based on polar coordinates. This slide briefly discusses how the points will be plotted. For more details on the golden spiral algorithm, please refer to the citations. Now my partner Tal will conclude our presentation.
Thank you, Sahil. As you can tell, we initially set out with some particular objective that had to change along the way. We have learned a lot about what it really means to work in creating a particular simulation model and some of the challenges associated with it. This has been learning experience and we hope you have enjoyed our presentation despite its limitation. Here is our reference and resources that help us achieve this project. Thank you.